Welcome guys, today we'll be implementing super fast hash set in C++. So let me just quickly walk you through the architecture that we'll be using, and then we'll be working on that C++ implementation. I will be showing you the C++ implementation. Okay, so architecture we will be using is a table belonging to a log. Okay, so the architecture is really simple. We will be having a table of a key belonging to index. I will be telling what index. Key belonging to index. This table will be living inside L1 cache. It will be really short table in size, so it will be living inside the L1 cache, and we'll be having a contiguous block of memory inside the heap, where we'll be storing the value in append only log. So what is a append only log? Basically you cannot insert or delete in between. You can only insert or delete at the end of the log, and append only log only allows you to append. So inserting is only allowed, deleting is not allowed, but we will allow deleting too. So we will be having all the values stored like this, and they will have their corresponding index I. So like I1, I2, I3 and so on. Instead of storing key belonging to the value, we will be storing key belonging to the index. So we will be having something like key 1 belonging to index 1, and key 2 belonging to index 2, and so on. And if we want to check if a key exists, we can just check this table. If we want to retrieve, then we can retrieve from the append only log, and both of the operation will be O of 1 in time complexity. Why is this better? Well, because this uses contiguous block of memory that is cache friendly. So normal unordered map in C++ uses linked list for storing the key value things. So if you want to retrieve value, you have to do random access, so you get lots and lots of cache misses. But in this thing, since this is contiguous, there is super low chances of cache misses. It will only happen when you will access the things super randomly, and if you're using smaller value types like integer or characters, then CPU will fetch almost 64 to 128 of those values at a time to store inside the cache. That is super fast. Also, a normal CPU cycle, so a normal lookup from the L1 cache takes around 3 to at worst 4 CPU cycles. So if we are checking if a key exists or not, if that's only what you are checking, then you are done in 3 to 4 cycles. And if you are inserting, then it takes around 700 to 600 CPU cycles. So let's take 800 for the upper bound. And since the table actually lives in L1 cache, so the lookup is actually super fast. And if the table lives inside the heap memory, then it will be taking 700 to 800 CPU cycles. So it's almost 200 times slower on the heap compared to on the L1 cache. Okay, so that's one thing. And yeah, this is the architecture that we are going to use. Let me just sum this architecture really quickly. So we'll be having a table inside L1 cache that will have a key and an index space. So how are we going to implement this table? This table will be a struct. So this table will be a struct of elements. What are these elements? Well, if these elements will be having a uint 8t, so to uint 8t key and value, so both will be uint 8t, so it will be 8 bits of memory for key and 8 bits of memory for index. So in total this thing will be 2 bytes in size. For the contiguous block of memory, it's just a simple append only log. So you have to have a contiguous block of memory, and you can only insert at the very end. That's it. You cannot remove, you cannot shift, you cannot do anything. And we'll be also storing the last index that was empty, so the insertion is actually O of 1, because we already know the last index that was empty. So yeah, that's it. Let me just tell you the implementation of our append only log. So just quickly go here, and yes, so this is the implementation that we are using. So this is a table element thing, and this is the template table. So also one more thing, if an element takes only 2 bytes, well, it could take any bytes. If you want, you could have an element take 8 bytes, but it will reduce the number of elements that you have in your L1 cache. So hence your table will shrink in the number of element terms. It will still be larger in size, but it will store less elements. So suppose you are using 2 bytes for your element, and your table consumes 16 kilobytes of L1 cache. You will be getting 8192 elements to work with, and this is a good amount of elements to work with. And you might ask, well, what if the table overflows? What if I need more elements? Then those elements will be allocated in another table, or I will be implementing something that will create a new table on the heap. So yes, it will be slow, but who cares right now, when we have, because in general purpose things, in general usage, 8,000 elements are way more than you would ever need, and they are super fast. So if you are suppose building a game, and you need to keep track of a player and their player data, then 8,000 players simultaneously are way more than you would ever need. But if you need, you could I will actually implement a method where if the table overflows, it will use another table to store the data that will still live in the L1 cache. So that's it. And we could actually increase this size, so it will not fit inside L1 cache fully. It will take the L2 and L3 cache too, but they will still be fast. They will still be under 50 cycles of retrieval and insertion inside the table, so that will be fast. So we have this thing right here. We are having its own hash table reference. So this hash map doesn't live inside the L1 cache. Only the hash table lives inside the L1 cache. This can live anywhere in the memory. And what's the benefit of this not living in L1 cache? So first of all, we get the whole cache for the table, so our table can hold more elements. And second of all, this hash map doesn't actually needs to live on the L1 cache. It has many functions, and it will just overflow the L1 cache, because L1 cache isn't just for our purpose, it is also handling the things from OS side and from other apps, so it will systematically overflow quite fast. So we have relied on only having the hash table on the L1 cache. So we will be having only the hash table on the L1 cache, and we will be having a control unit somewhere in the memory that will be controlling these two things. Okay, So we have just implemented a get hash data thing, and we are resolving, and that's it. So it's quite naive implementation right now. So we have operators overloading, and we have an insert method. That's it. And here I have quickly made a benchmark kind of thing that will help us get an idea of how fast is this thing. So if I go, let me just go, sonic hash map insert took 4 milliseconds, unordered map took 10 milliseconds approximately. The lookup for our sonic hash map was 3 milliseconds. Iteration was 0.1 milliseconds. So it's the unordered map is almost 10 times slower. Here it's 2 times slower, here it's 2 times slower. And we have the verification sums right here. So as you could actually see that our sonic hash map is actually a bit faster, and you could see the number of elements that we tested were 40,000. If I increase this, okay, so I have to make some changes. So I made the 400,000 elements to the nearest power of 2, that's 2 raised to 19, and I have to change these two lines. So I have to make the global hash table of 2 raised to 19 bytes, and same for this thing, and 2 raised to 19 bits, I guess, whatever it is. The total size of the hash table is actually around 4 megabytes, and this won't live in the L1 cache, because L1 cache maximum size is just 32 kilobytes or 64 kilobytes. So obviously this will be living in the L2 or L3 cache, or even in the main memory. So now let's test this. So that thing just froze, and I got suspicious that there's something wrong, so I just checked that. So let's go and run that. Okay, so now when the real data came, the iteration for us was faster, but now our sonic hash performed worse because the hash table now lives inside the main memory. So yeah, this is the trade-off. It is nice until it isn't. So the limit to the things. So now our table is 10 times slower on iteration and lookups, 10 times slower. Lookups on insertion, iteration it's faster, but if lookup and insertion are slower, then who cares about iteration? So yeah, this is the thing, and why it became so slow is the fact that we have lost the super fast lookups of L1 cache. So until your table is inside L1 cache, you are good to go, but as soon as it spills into L2 or L3 cache or in main memory, then you are in the red zone. So this implementation, obviously it is really naive. If I implemented this with somewhat more dedication, it will be better than 1 and 2 seconds of lookup. So yeah, this is it. And actually this thing made me learn so much, because up to a certain point you can beat the C++ implementation of unordered map, but after a certain point unordered map will be more efficient, and it will be just easier to use an unordered map than to write your own. And it has actually been super optimized, and my code, I'm pretty sure it isn't optimized in any way, but it is what it is. So I'll be seeing you guys in the next video, and yeah, that's it for today. Bye.